Next up, we have Tom Donnelly, who is with us from the JUMP Statistical Discovery LLC company. And I don't think it would be DataWorks if Tom wasn't here doing a talk or teaching a course. He has a tremendous amount of knowledge that he's going to share with us today. And today's going to talk to us about, is that different than this?
It does look different, but
it does look different.
Read yours,
you want me to read this one?
Read that one.
But am I going to read it and you're not going to talk about it?
No, it's the same talk. Same talk, different title.
Okay. He's going to talk to us about using sensor stream data as both an input and an output in a functional data analyses.
Well, slides are coming up. Well, thank you, Denise. I'm also a physicist by training, but I don't know if I'm reformed, and so I do need to talk to Jim about exactly what is involved with that process. So I see IT is coming up. Do I need to do something? Okay, so the only difference in the title that Denise read and what is up here is rather than just saying generically sensor stream data, I'm specifically using a glucose monitor, so it's a glycemic response model. But otherwise, it's still about functional data being used as both an input and an output from a model. And so this is what we're talking about. In this case, we're collecting data from a patient. So the curve in the yellow box is the response over time to their glucose level after they've eaten a snack. Okay? We want to be able to predict the shape of the curve. Okay? So here's what we do. We have these wearable monitors, and for 10 hours they fast. And so the blue baseline is what we collect, and then they eat a snack, so there's pictures of several of them there. And then once they've eaten it, you get the red curve, which is the response. And so what we're interested in is using the information of the blue curve and the snack as the inputs to the model so we can predict what happens after that. So, you know, this is a DoD conference, and I would say it was maybe the last in-person DataWorks where we gave a couple of talks on functional data analysis. And there's a broad number of sort of sets of data. I think I see Dr. J out there. I think I talked with him about this maybe 5 years ago. But you've got sensors on aircraft, okay? Think of that as that could be your sensor. It could be radar. It could be sonar. But the point is, we've got a shape of a curve is where the data is. It's not just a point, okay? So this is just a data set that I could get my hands on to do that kind of analysis, okay? So here's sort of the details overlaying all 91 patient snack combinations there. It looks pretty messy. So you've got all these baseline curves when they're fasting, then they eat, and then we get the post-snack response. And so this is what we're trying to model. And here's kind of the average of the all of these snack patient combinations, both the before and after. So you notice time goes from minus 600 to 0. That's the 10 hours before, and those dots are all 5 minutes apart. And then from 0 to 240 is the 4 hours of measuring the glucose response after they've had their snack. And so here are the 20 patients, each eating 3, 4, or 5 snacks. And the ones highlighted in yellow are going to be excluded, and we'll use those to test how well the model works. And you'll notice that some of the folks seem to have a lot of variability, others don't. Some have a single peak, so maybe here this explains that a little better. You know, some people have moderate variation, some have very little, some have quite a bit, some have 1 bump, some have 2 bumps in their analysis. So the curves are not all the same, even though on average, you know, it looks pretty tame. Okay. So again, what is functional data analysis? It's a branch of statistics where we analyze data providing information about curves, surfaces, or anything else varying over a continuum. In its most general form, under an FDA framework, each sample element is considered to be a function. So really, when you see the dots in the Y column on the functional data on the right, even though those might be discrete measurements, we really think of the curve as our fundamental unit here of observation. And so we have traditional rectangular data on the right. We've got some batches of material. We're controlling X1 and X2. Maybe we measure Y, and we fit models to that. Well, now we're substituting for Y as a number. we're actually substituting a curve as a response. And in this particular case, the x's can be curves as well. Okay? Now, I've been reusing this slide from David Harrison of Lockheed for several years. When he first saw functional data analysis, he went back to a program that, what little bit I can tell you about this, because I've never really seen the data myself, is this is missile flyout data for a family of I'll just say missiles that developed over 30 years. So, there's like a Block 1, a Block 2, a Block 3, and so over time, these missiles are changing somewhat, and they want to know, is the performance still within family? And so I think he told me that Lockheed, maybe another vendor or two, the Navy and Johns Hopkins Applied Physics Lab, all worked on this problem, and at the time that they did it, they used what you would call data landmarks. In other words, we can see there are different peaks, different slopes, delays in this curve. And so what you might do is say, what's the peak? What's the average of peak 1? What's the average of peak 2? What's the area under the curve? In other words, we use all these summary statistics of the curve, not the curve itself. And so once he saw the functional data, he applied it to the same problem and said, boy, it really worked out well. And of course, he couldn't give me the data. But fortunately, Joe Warfield, is he here? He's at the conference, but maybe not in the room. He was able to actually show me the analysis because he had the data. And what was really interesting was, and you'll see this coming up shortly, when we do the analysis, we get out what we call FPC scores. But each of those scores, you'll look at it, and it's sort of like a straight line relationship. But adjusting those, you can sort of tune how high a particular peak is or how steep a particular slope is. So we're actually going to see that we're able to model something like this to a much better degree. So if you're currently looking at data and you see a curve and you start doing these sort of landmark analysis, you're probably a good candidate for functional data analysis. So here's how we do it. I think I'll use the laser pointer here. So up here you can see we've got a bunch of data versus time. And it starts out that everything is pretty constant. And then after a certain point in time, we start to see variability. Okay, so the red line here is just the average through the data. Okay, these are each of the individual batches here. So what we do is we fit a spline to this data. Okay, so over here, this is showing you where we're using the Bayesian information criteria to tell us that the best performing spline happened to be a 4-knot cubic spline. Okay, so that's kind of the best empirical fit to the data. Then we take that spline and we do the functional data analysis. And what that's going to do is split these curves into, we'll call this a shape function. This explains the longitudinal variation. And then this is going to explain the function-to-function variation. So what you can see here is we've got a mean to the data. And you can see the standard deviation is pretty much near 0 up until about time 5, and then it starts to go up. Well, that's the nothing changing, and then all of a sudden things start to change quite a bit. So move along in the slide here. So what we're going to end up being able to do is we're going to be able to take these FPC scores, and we're going to be able to multiply them by the shapes. So this is sort of a weight for how important this shape is. When we add that to the mean, we're able to reproduce any of these curves. And in this case, we can see that 92% is really, this curve right here explains it. So what you're really doing when you multiply this curve by a plus or minus number, you're either adding, sort of a flatter shape or a more steep shape to this mean, and that's sort of what you get here. This is a steep shape, and that's a rather flat shape. Okay, so I have this cartoon to try to illustrate this a little more closely. And so what we've got here across the top is the mean and the 3 shape functions, the eigenfunctions. Okay? The next row has the shape function multiplied by a particular function weight. So that's in here. These weights come from each of these individual curves. So it's really dependent upon which weight you're going to multiply by, and then we add all of that to the mean. So what we want to do in the end is reproduce this function. Okay, so that's what's going to show up here, and we're going to get there by adding these various shape functions here to the mean. So we start with the mean. We're already pretty close, but I hope you notice there's a bump on the end here, but no bump here. But if I take this shape and I multiply it by its proper sort of scale function here, the 0.05, I get a little bump. So if I now add that to this shape, you can see I'm doing a good job of reproducing this end. But you can see this curve is clipped a bit more than this curve is clipped. So this, if I take this one, multiply it by its appropriate weight, you can see I can kind of get rid of that clipping on the end, and finally I've got just this little wiggle left. And if I multiply by that, I've essentially now completely reproduced this shape by taking the eigenfunctions or the shape functions and multiplying them by their proper weights. Okay, so that's kind of the key to how functional data analysis works. And so that's what we're going to... This slide is... I guess as a PDF, this slide doesn't build. So I guess I'll just have to explain to you. Behind this plot in the middle is the before curves, and here are the after curves. And these are the function summaries for the before, the snack, the function summaries for the after. And the model we build is we need both of these pieces of information to build the model to predict the after FPC scores. Okay. This will probably illustrate it a little better. So here's the before curve, and we've generated these FPCs. So depending what I multiply by, I can reproduce any of the patient snack baselines. Okay? Now, if I have to see how well can I predict a new patient, what we're going to do is take these FPC scores, and those come down here, and those are the multipliers that end up affecting this shape. Okay? So... again, that did not build. But the other thing that's in this is the snack. And you can see the snack doesn't make that great of a difference. Okay. Any questions so far? Because we're almost done. Yes?
So, two questions. One is, when you're building your eigenfunctions, are you choosing them by hand, or is there a prescription for that you're using?
So the question is, if we're building our eigenfunctions, is there a prescription for that, or are we building them by hand? There's a prescription. It's doing essentially what functional principle, well, if you've ever done regular principal components analysis, it's very analogous to that. And so there's the seminal work on this. This is where the other talks that I'll reference here at the end can give you a lot of the original work on this, but Ramsey is the original person on this work. You'll find a lot of publications in that. But yeah, basically, you know, it's completely analogous to principal components analysis. So it's rigorous. It's not a hand waving, we'll make these shapes.
And the second question is, are these eigenfunctions then all mutually orthogonal?
Okay, that's a question. The question is, are these eigenfunctions all mutually orthogonal? And I don't know. I would have to get one of our developers. Oh, I have one of our developers nodding her head yes in the back. So thank you, Elizabeth. So yes, they're orthogonal.
Well, actually, I have a quick question. So this reminds me of wavelet decomposition as well. Is there a crossover between this and wavelet analysis?
So the question is there a crossover between this and wavelet analysis? And the answer to that is yes. So I'm showing the analysis being done with JUMP, and our next release in October will add wavelet analysis. Currently, we do Fourier basis functions and various types of either penalized splines or non-penalized splines, but we're adding wavelets, and from everything I've heard from development, it gets way better. Okay, so that's, you know, kind of the way this works. We take these curves, break them into two pieces, shape and weights, and then from that we can build models. And here's the end result of this. So these were, if you recall, I had 4 people. If I go back here enough. These 4 yellow sets of curves had nothing to do with making the model. So now, when I'm done, I want to take the model that we have here and plug in somebody who wasn't in the making of the data set. Okay? And when I do that, this is 4 snacks for patient Eric. And so the blue dots and the thick line is the actual data. and the thin curve is what was predicted from the functional analysis. And some are clearly better than others. Interestingly, to me, this particular patient sometimes had only one peak and sometimes had two peaks in the actual. And that's just the variability in the patient. So I look at this data set more from the, making sure people are aware that you can now do functional data analysis on the input to make a prediction on an output as well. And down below here, if this were interactive, you could actually come in here and take one of these glucose monitor scores, and as you move it from left to right, you move along this line, you'll see these peaks go up and down. And so when I mentioned the Lockheed Martin slide before, that's where you would have several of these eigenfunctions, each associated with different parts of that curve, and you could drive up a particular point or a peak or down or a slope. And so in that fashion, you were able to capture all of the variability in that missile flyout data. And so the rest of these are just other examples. Again, some I would say have done better than others. But overall, this is the alternative to just what was the average peak height, and trying to predict just one point on that curve. Now we're actually able to predict the curve. So I wanted to point out that when we were here 3 years ago, we did 2 case studies. And so I think maybe you might be able to see how this might be more relevant to what you're doing. But this was based on 2,000 wafers, where a company is doing what's called anodic bonding. So they're pressing a glass wafer onto the silicon, and so they're applying force, and there's vacuum, and there's voltage applied. So there are 5 sensor readings. And it's not until weeks later that they find that they've made a defective wafer. So what they were really interested in doing was, can we use the output of these 5 sensors to predict, did we just make a defective wafer, and decide right now to set those wafers aside and no longer process them? Okay, so that's one of the other case studies. The other is what we'll call a response, a functional data analysis where we're doing a DOE. So in this case, we want to try to predict those curves. And actually, the yellow curve, we're calling that the golden curve. This is a manufacturing process for a pharmaceutical where they're milling the particles, and they have a desired size and spec limit on what they want that particle to be. And since it's a company that wants to make money, they want to get in spec as quickly as possible and then stay in spec. So if they could make something like the golden curve, they'd be really happy. Now, they don't really make anything quite that good, but it now gives us a target to do optimization to find, at least within the data set from this designed experiment, what set of conditions gets us in spec as quickly as possible and keeps us there, and therefore we make more money. So those 2 examples, one of them, the functional data is the input. That's this case, is the other case, the wafer. And this one, the functional data, is just the output. And I wanted you to see that we could do both of those at the same time. So if you want to see those particular talks, which although they're not recorded via DataWorks, I have recordings of these available, and so I've put links into the talk. And so there's a 1-hour version where it goes into a lot of details, and then there are roughly 5-minute versions of each, just so if you don't have an hour. And I just want the story behind it. There's a 5-minute and a 7-minute version of those. So in summary, this glucose monitor data, it was from a panel of patients, were used to show how you can do functional data as both an input to and use it as an output from the same model. The glycemic response over time of the patients could be predicted using their baseline fasting curve and the type of snack consumed. Those were the inputs to the model. Functional data shows up in many forms, such as sensor data, spectral data, virtually anything in a longitudinal order. A couple other examples that I maybe didn't mention earlier. I know the French equivalent of the FAA actually models flights between Toulouse and Paris. They're modeling the shapes of the flights, and they're looking at things like noise abatement and fuel consumption, but they're using the curve as the data. I've also seen data where Army surgeons, they're trying to determine how well, they're trying to learn how to suture, so they're using synthetic skin. They've got cameras, and they're tracking the motions of the hands, and those motions of the hands turn into functional curves that, again, they can model and say this is the type of movement that leads to more successful suturing than not. So quite a broad range, and I hope that you'll look at your data and see if you have functional data and that you can apply this. So final bullet, these data, we currently often summarize them into what we call landmark analysis. That approach does not take advantage of all the data that has been collected, and it can lead to missing out on effects of the shape of the data. So thank you, and if you have any questions, I'll try to answer those. Doesn't look like there's any, Denise.
No, I would love to see you use jumps to show us like how you did some of this.
Well, I kind of consciously didn't try to do that in this particular one. I'm happy to show people at some time, but we're not really set up to do this. I don't know whose computer this is, and it's not on it. So, but if anybody does want to see that, I'm always happy to, set up a webcast and do that. So please contact me if you're interested in seeing how to employ tools like functional data analysis. Yes?
I have one question. Is there any kind of mapping from number of landmarks to number of eigenfunctions? And how many eigenfunctions can you manage?
Well, I can tell you that what we'll generally output is, I've seen as many as 10 eigenfunctions, and it does depend on the complexity of the shape. But if you look back to this particular output right here, you get a Pareto chart of how much is contributing. And so in this particular example for the glycemic response, I think jump will give you about 6, but then we actually give you a curve that shows you kind of, what if you only use 3? How good of an answer are you going to get from that? And it'll actually try to steer you to what's the best number. But, it kind of depends on the complexity. This is a pretty simple looking curve. So you can see that the first one gives you a 92% answer. I've seen somewhere the first curve is only giving you 50% of the answer. So I wouldn't say that there's a hard rule, but you can see with sort of a Pareto ranking how much of the answer you can get with a certain number of eigenfunctions. I think a good video on that would actually be the one on the anodic bonding, because the shapes of the sensor readings are pretty simple, but they're also almost like step functions at times. And so you can see that one FPC is totally driving the front edge of the step, and another one is totally affecting the back end of the step. So you can really see the isolation of each of the eigenfunctions to the sort of composite function that you get. Yes?
Is there a cutoff for what frequency of data would be considered functional data? So like 1 hertz, or it just depends on your outcome of interest?
Yes. The question is there a cutoff on frequency? And I would say you could probably do this on annual data, annual temperature data. And it's going to cycle over 12 months at a particular latitude. So people could do functional data on stuff that, lasts a year. But you could also have something, so the range, it's really what's your range of interest? And the same is true. You can do it with wavelength and frequency. It doesn't just have to be time. It could be anything that you're interested in, the shape of behavior versus some other thing. So it could be versus a temperature, what's happening to a particular parameter.